Hey everyone, and welcome. Today, we're diving deep, and I mean really deep, into the hidden world of materials. We're going to explore the invisible architecture that decides why some things bend, why other things break, and, this is the cool part, how we can actually design the materials of the future from the atom up. It all kicks off with a really simple everyday question.
Think about it for a second. Why is it that you can bend a paperclip back and forth, but the second you put a little too much pressure on a cracker, it just snaps? I mean, they're both solid objects, but they behave in totally different ways. Well, the answer isn't something you can see on the surface. It's actually buried deep inside their invisible structures.
So here's our game plan. We're going to start with the world of materials that's all around us. Then we'll look at the properties we can actually see and measure. After that, we'll zoom way into the microscopic level and uncover their secrets. And then we get to how we use all that knowledge to design brand new materials. And finally, we'll get a little glimpse of what's coming next.
Seriously, just take a look around you right now. The chair you're in, the device you're watching this on, the building you're sitting in, every single thing is made of a specific material that was chosen for its own unique properties. Our entire modern world is quite literally built on the science of materials.
Okay, so when an engineer is picking out a material, the first thing they look at are its macroscopic properties. You know, the stuff you can actually see and measure on a big scale. How heavy is it? What happens when you pull on it or squeeze it? These are the big picture behaviors that really matter for performance.
And this is a perfect example. A simple property like density can make a massive difference. On the right, you've got your standard, heavy concrete. But on the left, we have lightweight concrete. It's a lot less dense, which makes it perfect for jobs where weight is a huge issue, even if it means you're trading off a little bit of strength.
All right, here's a really crucial concept for engineers. It's called the yield ratio. This number is key. You know why? Because it tells them exactly how a material is going to fail. It's basically a comparison between the point where material starts to bend for good, that's its yield strength, and the point where it just completely snaps, which is its tensile strength.
So what does that actually mean for us? Well, a material with a low yield ratio, that's our paperclip. It gives you plenty of warning. It bends, it deforms, you can see it's about to fail. But a material with a high yield ratio, yep, that's our cracker. It stays strong and strong and strong, and then boom, it just fractures suddenly with no warning at all.
And this right here brings us to the absolute heart of it all. All those big picture properties we were just talking about, they are all controlled by something you can't see with your own eyes, the material's microstructure. So let's zoom in.
You know, this is where a material really gets its personality. It's all about these tiny little features. How are its atoms arranged? Is it a neat, orderly grid, or just a big jumble? Are there tiny, invisible cracks just waiting to cause a problem? Every single one of these details, at the micro level, is what defines how that material is going to behave out here in our world.
And check this out. This is a fantastic example. Why do we use titanium for so many medical implants? It's because its surface at a microscopic level is just rough enough to encourage our bone cells, those are called osteoblasts, to actually grow right onto it. This creates a super strong, permanent bond. That's a life-changing outcome, all thanks to a texture you can't even see.
Or think about a huge slab of granite. You'd probably assume its strength is the same all the way through, right? Well, not exactly. Its real breaking point is actually determined by this whole network of tiny, invisible microcracks that are spread throughout the rock. The fate of something massive is literally decided by its smallest flaws.
So, if the microworld is what controls the macroworld, what if we could control the microworld? Well, that is exactly what modern material science is all about. We're now at a point where we can actually design materials from the inside out to give them the precise properties that we want. Take a look at this. It's really fascinating. By tweaking the microstructure, scientists created what's called a hybrid silicone-rubber concrete. Basically, they swapped out some of the hard, rocky bits for tiny particles of silicone rubber. And as you can see from the table, sure, they gave up a little bit of raw strength, but in return, they created a material with way more ductility and energy absorption. This stuff can bend and absorb impacts in ways that normal concrete could only dream of.
And the way they do this is, conceptually at least, pretty straightforward. You start with a base material, like concrete. Then you intentionally mix in a tiny amount of an additive just to manipulate that microstructure. We're talking about adding just 0.5% of plastic fibers or a little bit of silica fume, and that can fundamentally change the concrete's behavior, creating a whole new high-performance material.
And hey, this isn't just for some crazy futuristic lab stuff.
Just look at this chart for simple PVC elastomers. By making tiny tweaks to the internal recipe, manufacturers can create all these different grades with different levels of hardness. That's why the soft grip on your toothbrush feels so different from the tough sole on your running shoe, even though they might come from the same family of materials.
And this whole idea gets pushed to the absolute limit with something called functionally graded materials. Imagine a single piece of material where the microstructure on one side is engineered to be super hard and rigid, and then it gradually and intentionally changes across the material to be flexible and soft on the other side. That is the ultimate in micro-level design.
Okay, so let's zoom back out. Understanding, and even better, manipulating this invisible architecture of materials is unlocking a whole new future of innovation. The next generation of incredible technology, it's being built right now, at the micro scale.
I mean, just listen to some of this stuff. We're developing things like metal rubber that can absorb massive impacts. We can use lasers to basically print graphene for incredibly sensitive sensors. There are even smart, self-swelling materials that expand on their own to improve performance, and reactive materials that unleash chemical energy when they're hit.
And that right there is really the key takeaway. The path to building stronger bridges, faster computers, and safer cars, it doesn't start with bigger designs anymore. It starts by mastering the world of the infinitesimally small, the world of microstructure. So, I'll just leave you with this thought. For pretty much all of human history, we were limited by the materials we could find laying around. But now, we can create the exact materials we need. So the only real question left is, what impossible things are we going to choose to build with them? Thanks for tuning in.